So today we're going to look at section 5.3 and how to diagonalize matrices and how they're related to eigenvalues and their eigenvectors. So it's very easy to find powers of a diagonal matrix. As you know, a diagonal matrix just has non-zero values across the main diagonal and zeros everywhere else. And we're going to look at just a very simple example. So a diagonal matrix, a matrix D is diagonal. It's what I just said before. So D to the K is trivial to compute, and we can look at that. So if D is that, then D squared is going to be, whoops, let's go back here. D squared is going to be D times D, which is 5004 times 5004. And multiply the first row by the first column, you get out 25. The first row by the second column just gives you 0. Same with the second row and the first column, 0 times 4 and 4, 0 times 5 and 4 times 0 gives you 0. And then the second row by the second column gives you 16. So we start off with a 5 and a 4 squared. These two terms, the 5 and the 4, the numbers across the main diagonal, just get squared. So if I multiply that again by 5004, we would get really the same thing. We would get 25 times 5. I'm just going to write that as 5 cubed, or 125. 0, and then we have 16 times 4 for the last one, or 4 cubed. So this is what D cubed is going to be. So D to any positive integer is going to be 5 to the K and 4 to the K on the main diagonal, and the other values are going to be 0. Now, how is that going to be helpful to you? Well, if you had to take a value, take a matrix and raise it to, the 20th power, you don't want to have to write out all of those, but we at least know what the D is going to be. So if we have a non-diagonal matrix, the most efficient way of figuring out what that is to diagonalize a matrix and then figure out what is the general format for all of the entries. In the last section, we learned that a matrix B is going to be similar to matrix A if there exists an invertible matrix P, such that P inverse times A times P equals B, or A equals PD P inverse. Now, what the heck does that mean? Well, we're going to figure out, how this B is related to what we just did. So we have a non-zero matrix A, and we can figure out some matrix, some invertible matrix that we're going to have. So we want our matrix B to be the diagonal matrix. So at least we have this easy part that we can deal with if we know what the diagonal matrix is. And is it going to be a random diagonal matrix? That answer is obviously going to be no. If we have a matrix where we're talking about, so we're starting off with, first of all, we're starting off with an invertible matrix. It has to be square. We're going to find the characteristic equation for the matrix A and find those eigenvalues. So it's going to have these eigenvalues, the first, the second, and the third. And these may or may not be distinct. Sometimes they're going to be the same. So the first eigenvalue could be the same as the second eigenvalue. Now, what is really important, we have to find these corresponding eigenvectors. So each eigenvalue has an eigenvector. And as we're building our P matrix, this and it's going to be just a vector. As we're putting in that first column, that has to correspond with the first eigenvalue. And we're going to look at that in a second. And then they have to match up. That's the most important thing with this procedure, is they have to match up. And so the matrix P is going to have those values, P1, P2, all the way up to Pn. So form the diagonal matrix with those corresponding eigenvalues. And so we could have, you can use our eigenvalues to build our diagonal matrix. And as we have this, now we're going to make sure those match up. It doesn't matter which one you do first. I most of the time find my diagonal matrix first, and then I'm going to build it at the end. And we're going to check that A equals P times D times P inverse. So this is the important equation from 5.3. So we're going to say that this A is equal to PD P inverse. So we have this A, that's given to us. We're going to first of all find out what P and D are. So we're going to go back to finding our characteristic equation. Our characteristic equation, we're going to subtract the two eigenvalues across the diagonal, make that determinant equal to 0. So we have 1 minus lambda times 4 minus lambda minus negative 2 equals 0. And so we're going to solve that equation. And this is obviously going to give you lambda squared minus 5x minus 5 lambda plus 4 plus 2. So then we're going to factor that. That factors to lambda minus 3 and lambda minus 2. So we have our two eigenvalues. And at this point, the first eigenvalue is 3. And I'm going to color code these just to make sure. So we can go ahead and build our diagonal matrix. So we know what D is. So D, do this, is going to be, the first one is 3, the second one is 2, and all the other values are 0. So that's our diagonal matrix. So we already have D. And just as before, we're going to find the eigenvector that corresponds to 3. So in order to do that, we are going to throw that in. Throw in 3 in for the two lambda values. 1 minus 3 is negative 2. Positive 1 doesn't change. Negative 2 doesn't change. 4 minus 3 is 1. And so this row reduces. Augment that with 0 if you want to or wish to. And that obviously these two rows are going to cancel out. First row is going to stay. And I'm going to extend my page. I'm going to change my color back. And so this kind of says negative 2x1 equals negative x2, excuse me. And x2 is free. So what is going to be our x2 is equal to x2. So at this point, you can write this p-value as many ways as you want to. So we have lots of choices for this. We could write it as dividing both sides by negative 2, we get 1/2, and we have 1. Or I would rather deal with non-fractions. So I'm going to call that one 1, 2. So we have our p matrix. We have half of our p matrix. So our p matrix is going to consist of 1 and 2. And remember that was red, so that corresponded with the eigenvalue of 2. The next one, going to do that one a little bit faster maybe. When lambda is 2, I'm going to close that off. Maybe I can squeeze it in right here. If I throw in 2 into my matrix, then I'm going to have to A minus lambda is going to be negative 1, positive 1, negative 2, positive 2. Again, those two, this row is just a combination of the first row. So now I have negative x1 equals negative x2. And so that eigenvector, the eigenspace that corresponds to the eigenvalue of 2 is going to be 1, 1. So that is our p-value. Find matrices P and D such that so we have already, and this could be, you can make that 2 and 2 if you really want to. It is just whatever, so I'm stuck with this one, and so we're going to say that A, and we can check that, equals P, 1, 2, 1, 1, times D, and our D value, our D matrix is 3 and 2, times P inverse. So P inverse is 1, -1, -2, +1. And I'm going to take out my calculator. I'm going to check that that does give me that. And so when I take out my calculator, multiply those two matrices and the third one. Or you can put this one in as matrix A, matrix B, and you can write in do you get out A times B times A inverse, right? So that's kind of it with that. So I hit pause on that one for a second, and I was checking this because I was doing this in my head, and I realized, oh, the determinant for this one is going to be -1, which means that our A inverse, I forgot to multiply that by -1. So I'm just going to throw in a -1 right here, right, times -1. And so that will give me, so A inverse should have been, I'm just going to write that here, or P inverse, excuse me, should be -1, +1, +2, -1. Or take that whole thing and multiply by -1. And since it's a constant, we can do that. And I think that the notes might be, oh, actually I do have the negative in there. I didn't see it. So given we have this matrix A, find matrices P and D such that A equals PD P inverse. And so just be ready for this same thing that's going to appear on the quiz. And if you're following along with this, we should be all right. So I'm just going to quickly do this one. Oh, when we have a 3x3 matrix, actually I do want to show you, you have to be careful with this one. So I think that looking at the notes, I used this first row. So we're still going to factor out a 2 minus lambda. Probably not going to 2 minus lambda, 2 minus x. And then we still have this determinant of 3 minus lambda, 1, 0, and 2 minus lambda. So don't drop those minus x's or minus lambdas as you're doing your work. And we want that to equal 0 to find the eigenvalues. And so it actually becomes fairly easy, I think. Oh, and I want to make sure that is a positive. And then those are still going to be zeros. I'm going to factor out zeros for the rest. I just didn't do that. So we have 2 minus lambda, 3 minus lambda, and 2 minus lambda. So obviously our eigenvalues are going to be 2, 2, and 3. Maybe I will change the colors on that. So I have my diagonal matrix. As you're building this diagonal matrix, you can put the 2 and the 3 wherever you want to. I am just going to, you can split up the 2's. Or you can put the 3 first and the 2 and the 2. It's just that whenever you have this, now you're stuck. You don't have any other options. So we're hopefully going to get out 2. If it is diagonalizable, then we're going to get 2 eigenvectors that correspond with 2. And we're going to get 1 eigenvector that corresponds with 3. So we can find out what our P is. So if lambda is 2, now I'm going to go back and looks like that is green. So when lambda is 2, what we're going to have is we're going to have 0, 0, 0, 1 half, 1, 1, 0, 0, 0. All right, and so it's never a bad idea to go ahead and write it like that. And we can see that the only thing that really matters, we can switch the first and the second rows, then multiply by 2. And so what I have is x1 equals -2x2 minus 2x3. Just using that second row, augment it with 0. And so therefore our 2 free variables are x2 and x3. So x1, x2, x3. x1 is equal to -2 x2 plus -2 x3. x2, remember this is kind of factoring out the x2. This is in terms of x3. x2 is equal to x2 plus 0 x3. x3 is equal to 0 x2 plus 1 x3. Those two vectors are independent. And so therefore my P equals the first, and it doesn't matter which one you write first, -2, whoops, 1, 0, -2, 0, and 1. And we're going to do the same thing for x3 when lambda is 3. And then I'm going to go scroll up a little bit so I can see that. So we have -1, 0, 0, 1/2, 0, 1, 0, 0, -1. And then I'm going to row reduce that one. I'm going to use my calculator for that one. And what I get out is this 0, 1, 0 vector. So what this is saying is that when I row reduce this, I knew that x1 equaled 0, x2 is equal to x2, and x3 has to be 0. So that's the only way, and you can kind of see that right there when you augment it with 0. The only way this last equation is going to be true is if x3 equals 0. We have -1 equals 0. The only time that's true, x3 is forced to be 0. Same for x1. Okay? So that is it. And so hopefully as you're doing these, you are also, pausing just to make sure that your math double checks it, just like I did, because I always want to double check the stuff, the answers that I have. Make sure I'm giving you the right information. And I did, I paused it and I made sure that that one actually did work. And then we would just use your calculator to find P inverse. And then I didn't write out what P inverse is because we can all just throw this into the calculator, hit the x to the -1 button on the calculator to find out what P inverse is, and we can double check our work, right? So now we're going back to now if I want to find out what a to the k is, given that a is equal to PD P inverse. So what are we going to do with that one? Well, if we have this, then we know that a to the k, so these are inverses of each other, so this will always be the identity on that one. So a to the k, p times p inverse is always going to give you 1, or the identity. But they're not commutative, so a to the k is going to equal p times d to the k times p inverse. We still are going to keep these two matrices, p times d to the k times p inverse, and we can double check it if you really want to. So there it is right there. There was the note right there. So we know what d to the k is. So a to the k for any power is going to equal 1, 1, 1, 2 times d to the k. And then maybe we'll come back and we will throw in we'll let k equal to something simple like 3. And we can check our math on the calculator. And so this one is, to find the inverse of this 2 by 2 is pretty easy because the determinant is 2 minus 1, or 1. So all we have to do is switch the 2 and the 1 and negate the 1s. Okay, so what is going to be our general formula for this? So what I'm going to do is I'm going to multiply the first row. Multiply these two things first. They're not commutative, so we have to do them in order. So we are going to have a to the k, first row by the first column. Oh, that's nice. It's just going to give you 5 to the k times 1 plus 0. First row times the first column. First row by the second column is going to be our entry, and whoops, I said I was going to call it, I'll call it 3 later. So it's 4 to the k. First row times, second row times the first column is still going to give you 5 to the k. And then the last one is going to be 2 times 4 to the k. Order of operations says that does not become 8. You have to do that exponent first. And now we're going to multiply that by 2, -1, -1, 1. And we are going to get, now the first row times the first column gives you 5 to the k minus 4 to the k. So it does take like a couple of steps, but it's if you had to take that a to any power, you didn't know what was coming, then it would be good to have this formula. And then you could do it by hand and etc. So first row times the first column. Whoops, I left off that 2 right there. And then the first row by the second column is going to give you negative 1 times 5 to the k plus 4 to the k. And then the second row, still going to have 2 times 5 to the k. And then we're going to have minus 2 times 4 to the k. And then the last one we have is negative 5 to the k plus 2 times 4 to the k. So now, if I wanted to find out what a cubed was, the way I would check it, honestly, is with a calculator. And so we have this general formula that we can use. And I'm going to go ahead and press pause. I'm going to know what a cubed is, like in one step. Or I should know that it should be the same thing as if k is 3, then I might be able, it should give me, my calculator should give me whatever 2 times 125 is, I'll call that 250, minus 64. And then we have negative 125 plus 64. 2 times 5 to the k is still going to be 250 minus 2 times, that's what's that, 128? Negative 125 plus 2 times 64 is going to be 128. So I can do that one very easily. It should be a positive 3. I'm going to press pause. I'm going to check my work. So now back, and I actually used my calculator, put in matrix A, and then I said raised to the third power. That did, my calculator told me that was 186. That makes sense. Minus 61, that looks good. 122, that looks good. And 3 looks good, right? So that is what a cubed is, and you can do that for any power. A to the 5th power, a to the 10th power. So that was a way, if you get it right here, you can now figure out what a to the 12th power is. Why is that useful? Well, it's kind of going back to our steady state vector and what's going to happen after we run this thing 100 times. What is that matrix going to look like? Okay? And that would be kind of different for depending on the problem. But that would be a way that you could do that. And so I did to the 3rd power of that same one. I am not going to really do this one. You can do this, first of all, you can do that with a calculator. And then when you can check your formula by making sure, but it's still a great idea to go ahead and get our D values for this one. And so I'm just going to real quickly tell you what your eigenvalues are when you do this. Your eigenvalues are going to be -1 and -2, right? When you do 1 minus lambda times -4 minus lambda plus 6 equals 0. That works for -1 and -2. And so my D matrix is going to be -1, -2. And then I will just make sure that that's our D matrix. Whoops, that should be blue. 0, -2, 0, -2 is that one. And so our P matrix, we can get that one by throwing that in. And the eigenvector that corresponds to -1 is going to be 1, 1. And the eigenvector that corresponds to -2 is going to be 2, 3. Okay? So A is equal to PD, P inverse. So I know what P is, I know what D is, and I can easily find what P inverse is. And A to the 10th power is going to be, so even though we're raised to the 10th power, it's not going to change your eigenvalues in that case. We're still going to use -1 and -2. So the P matrix is going to be, change that to black, why not? -1 and, whoops, +1. Look at the wrong one, which is erase that one. 1, 1, and 2, 3. So, and then again, I cannot emphasize enough how important it is that those two things match, and also that this is the eigenvector that corresponds to -2. And then we'll complete our clean up sum notation, and then whatever P inverse is. And again, that one is easy. 3 minus 2 is 1. So all we'd have to do is switch and negate, right? Switch and negate. So that's it. And then we know what -1 to the power of 10 is. -2 to the power of 10 is a little bit more difficult. And then we would check that. And do we get what a to the 10th power is, right? So if you're doing this on the quiz, if you happen to have to do the same type of problem on the quiz, what I really need to see is what the p value is, what the p vector is, what the d vector is, what p inverse is, and then the final answer, right? And how you got that. You did a to the 10th is going to be p times d to the 10th times p inverse. So a square matrix A is said to be diagonalizable if it is similar to a diagonal matrix. Basically, if you can get this, A is equal to PD, P inverse, where P is invertible, and D is a diagonal matrix. When is it diagonalizable? And I think I just said that maybe because I was ahead of myself a little bit. So first of all, we have to have that matrix is going to be diagonalizable only if it has n linearly independent vectors. And if an eigenvector has a multiplicity of 2, then I'm going to have 2 eigenvectors with that one. If it doesn't, columns of n and those eigenvectors are going to be linearly independent. The diagonal entries of D are going to be the eigenvalues and correspond respectively. And that's what we saw in like slide 3, honestly, right? So if I have an eigenvalue, I have to put in there twice, then I'm going to have 2 eigenvectors. Why is this thing diagonalizable? Well, first of all, since it is a triangular matrix, it's really easy. We have 3 distinct eigenvectors, 2, 6, and 1. And each of those 2, 6, and 1 are going to have 1 eigenvector that corresponds to them. The eigenvector, just because I've already done it, the eigenvector for 2 is going to be 1/2, -1/4, and +1. And that is perfect, right? We do have 1 eigenvector. They have 1 free variable when you throw in that 3. Sorry, when you throw in the 2, you get out 0, 0, 0, 2, 4, 0, 3, 2, -1, right? And then our x3 value is going to be our independent vector, independent variable, a free variable. You can leave it like this, or you might want to go ahead and multiply the whole thing by 4, and that would give you 2, -1, +4. Or it could be -2, +1, -4. It does not matter. That is still going to give you the eigenvector for that one. And again, what that means is that if I take this, we still have A times X, our eigenvector, is equal to lambda times X. Okay? So if I take this matrix A and I multiply by whatever I want to, if I multiply by that one, what I'm going to get out is going to be 2 times this. I'm going to get out a 1, -1/2, 2. That's what I know. By the way, just going back a little bit to 5.1. The eigenvector that corresponds with 6, I can't read my handwriting. It looks like a 0 and a 2.5 and a 1. And so we are going to have 1 free variable again. And in each of these cases, x3 is our free variable. And those 3 vectors are linearly independent. Okay? So that's what we have. We have 3 eigenvalues, 3 eigenvectors, and you can check that they are linearly independent. Linearly independent. So in that case, there are no free variables if I were to mush these three vectors into one P matrix. They are, or you can just hit the inverse button once you throw those in. Okay? So it has, so if we do have distinct eigen values, it is going to be diagonalizable. We don't always have to have this. It's okay sometimes to have a repeating eigenvalue. In this case, it is not, because I have only one eigenvalue, excuse me, and that's lambda is 2. We have 2 minus lambda times 2 minus lambda, and it has a multiplicity of 2. So if I throw this in, I get out a 0, 0. This is a minus lambda. And across the diagonal, you know what I mean, I hope. And we have 1, 0. So what this says is that x1 is equal to 0 and x2 is free. So we only have one eigenvector, 0, 1. But we need to have 2 eigenvectors, and we don't. So this one is not diagonalizable. We don't have the P. We don't have P. We do have D, right? Our D would be a 2, 2, 0, 0. But since we don't have a P. P does not exist. We only have one eigenvector. It has to be a 2 by 2. Okay? Diagonalize the following, if possible. Well, what I know is that I don't have 4 distinct eigenvalues. I do have 2 distinct eigenvalues. This already is triangular, so that makes our life a little bit easier. Hopefully we're going to get out 2 eigenvalues if it is diagonalizable, and the other one is going to be lambda equals 2. And at this point, you might want to just double check that my math was right, or that your math is right, or you know how to do this, right? Just real briefly. Well, you don't, and then we are going to need that minus lambda across all of them to decide whether or not we have to throw in each of these lambda values to find whether or not we do have 2 distinct eigenvalues. And we do in this case. And it does say to diagonalize it. What does that mean? That means that we need to have A is equal to PD P inverse. Okay, so with scratch work, we already have that middle value. We have -2, -2, and we change the colors on you, 2, 2, and everything else is going to be a 0, 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3 zeros. So as I'm building the P matrix, I'm going to do that kind of a scratch work. And I'm going to throw in that -2. And so we are going to have -2 minus -2. We're going to have 2 rows of zeros. 1, 2, 3, 4, 1, 2, 3, 4. And then we're going to have 24, -2, -12, excuse me. And then we're going to have 4, 0, and then 4, and a bunch of zeros. I can see, and maybe you can also, that, which values are going to be free. I know that the only way we can get non-foolishness is if x4 is, that fourth variable has to be 0, right? And we're going to have 2 free variables. And the way this looks when you throw this into the calculator and row reduce it, you are going to have a 1, 0, -6, 0, and you're going to have a 1, 2, 0, 0. So when you row reduce this one, you probably got something that looked like x1 is going to be free. x2 is also going to be, actually, I'm not even going to lie to you. I can't back engineer that one, but I do know that those 2 eigenvectors are going to be the ones that correspond to lambda is -2. When lambda is +2, the 2 eigenvectors that you get out are going to be 0, 0, 1, 0, and 0, 0, 0, 1. So that one right there I can do. So x3 and x4 are free. x1 and x2 both have to be 0. Okay, so that's what P is. And there's my D. And I'm just going to say times P inverse, right? We already have P. We can use our calculator to find P inverse. And that is now diagonalizing that. And you throw that in, P times D times P inverse, it's going to give you back A. Okay? So I did get out 2 eigenvectors for each eigenvalue that I had. All right. So we have, if we have distinct eigenvalues, each one of those are distinct. So this one does only have 2 distinct eigenvalues, -2 and +2. The dimensions of the eigenspace is going to be less than or equal to the multiplicity of the eigenvalue. That's always going to be the case. If matrix A is diagonalizable, if and only if the sum of the dimensions of the distinct eigenspaces equals n, and this happens only if and only if the dimensions of each eigenspace equals the multiplicity. And it's kind of the same thing that we were saying before. So that theorem kind of already talked about it. Okay? A is diagonalizable, and if A is diagonalizable, and we have a basis for the eigenspace that corresponds to that same eigenvalue, the total collection of those vectors forms an eigenvector basis for R. So basically, what this is all talking about, as I understand it, is P. P is formed up of those bases. And so if we go back and look at P on that other one, these are still going to be, as we kind of know, independent vectors, right? And this is going to be the bases, B1, B2, B3, and B4, right? We can throw those together and that forms a basis. You can think about them, and most of the time I just think about them as one big matrix, not necessarily as a basis. So that theorem is like the last thing, and just a way you can double check. And if you were paying attention and doing it along and having your calculator out, maybe pressing pause a couple of times on the video, then you would have seen all those things, okay? If you have any questions, please reach out to me and I'll be glad to answer those. Good luck as you do the quiz for 5.1 through 5.3. 5.4 and 5.5, they're not going to be quizzed. I haven't decided whether I'm going to throw those in as extra credit type problems. So good luck. Again, if you have any questions, office hours, or send me an email.